All right, so um, let's look at how we can create how we can estimate population proportions. Okay, and so the idea is always this: we start with a proportion that we get from a sample, and then we use that to estimate the proportion. That's what we always do. We're using sample things to sample statistics to estimate population proportions. There are three ways we can do this, or two ways we can do this. Either we use a point estimate, and um, and that basically just means we use the p hat from uh, the p hat from our sample, and we just say, hey, we therefore think that the population proportion is p hat. So the population proportion is p. So we're basically saying p is going to be approximately p hat. Pretty simple. You just use the number you get from your sample. The other thing you can do is use a confidence interval. This has the advantage of giving you a range of values, so there's a better chance that you've actually included it, and it also gives you the ability to include in that range how confident you are. That's really nice. You're able to say, I'm 95% confident that the true population proportion lies in this range. All right. And then finally, we can actually work this process in reverse. If we can decide how close we want to be, or I should say, if we know how close we want to be before we begin the study, then that'll tell us how many people we need to estimate in order to get that area. All right, so we'll demonstrate those as we go along. Okay, so the point estimate, it's a single value that we use to estimate the population proportion, and the best point estimate is p bar or p hat. That is the number that we get from the sample. All right. A point estimate, with the reason we like to use p hat as a point estimate is because it's unbiased. In other words, when we start finding sample proportions, they're going to almost always land in the area of the true proportion. All right, so it's going to give us a consistent estimator. Remember, an unbiased estimator is one that targets the population parameter. All right, we've talked about that. So in other words, sample proportions should be in the ballpark of population proportions. So let's look at an example. Right, here's a real quick example. So suppose we took a poll and asked 1,487. So that's n equals 1,487. We asked them, and 43% of them said they have a Facebook page. Okay, 43%. So the reason we're doing a poll is we want to be able to say what's the proportion of all adults who have a Facebook page, right? And so the way we do that is by asking these 1,400 people. And so, but we really want to estimate the population proportion. So the way we can do this is one way is to use the point estimate and to use that 43% that we got from the sample and just say, therefore, we think that the population proportion is 43%, right? The 43% came from our 1,400 people. We're going to just go ahead and turn right around and say that 43% is how many of the entire population. That's the point estimate. Okay, but let's look at a confidence interval. So in a confidence interval, you're not going to give just a single number as the population proportion. You're going to give a range of values. You're going to say, I think the population proportion is between these. And in addition to this, not only are you going to give the interval itself, but you're going to state how confident you are in this. This is called the confidence level. All right? We have some confidence levels that we've got. And a lot of times we'll use the Greek letter alpha in conjunction when we're talking about confidence levels. All right? So alpha is what's called our significance level. So 1 minus alpha, as you can see in this formula, that's our confidence level. You just take 1 minus alpha. So if you're trying to create a confidence level with a significance level of 0.01, then 1 minus 0.01 is 0.99. That's your confidence level. All right. So that's what that's what the alpha is. All right. That's how confident we are that the interval contains the true proportion. And you can see these things right here. Here are your corresponding alpha levels, and these are the common confidence intervals, right? Pretty much 1 minus each of these gives you your confidence level. Okay, so there are some ways to interpret this. So let's just look. Here's a confidence interval right here, 0.405 to 45. So I'm just going to make it simple, I'm just going to refer to this as 40% and this is 45%. And so we're saying P, which is the population proportion, is between 40% and 45%, right? So here is the correct way to interpret a confidence interval. And this was the 95% confidence interval, okay? So here's how you interpret it. We're 95% confident that the interval from 40% to 45% actually contains the true value. Okay? That's the language we've been using, so it's not a surprise. We're 95% confident that this interval contains the true value of P. We don't know exactly what it is, but we're 95% confident that it's between 40 and 45. All right? Now, here's a wrong way to say it. There is a 95% chance that the true value of P is between 40 and 45. It's a subtle difference, but it's not a chance. We're not expressing a probability here with a confidence interval. We're stating how confident we are, right? And this is an idea that we use all the time in our regular life, way outside of statistics. I'm 90% confident that I am going home this weekend. We know that kind of conveys the idea that there's a really good chance that we're going home, but not a probability. We don't use the chance. We just use how confident we are. So we don't want to get those two things intertwined. If we continue, here's another incorrect way. 95% of sample proportions will fall within 40 to 45. That is not true. That's not what we're saying. We're just saying we're 95% confident that the true proportion falls. All right. So here you go. Here is an interesting graph, all right? So when we create a confidence interval, it tells us that the process we're using should, in the long run, result in a confidence interval limits that contain the true proportion 95% of the time. And so here's what you see in this graph is that these are actually confidence intervals. Each of these little dots is a confidence interval written vertically. So this particular confidence interval runs from about 47 to 53 or 40, somewhere in there, right? P is the true proportion. Notice if P equals 50, if P really equals 50, then this interval covers it. It catches it. So if we claim that our interval is 47 to 52, bam, we are right. P is in there, right? 50 is between 47 and 52. Move to this one. This one is 48 to 53. Again, this confidence interval catches the true proportion. These confidence intervals are constructed the way that we will describe here in a little bit. And notice, whenever we construct a confidence interval, these pink ones, or purple, they vary. They're all different, but notice they all cover the true proportion. So they all contain the true proportion. This one time we created a confidence interval. It ran from about 43 to 47, and notice it does not cover 0.5. All right? So all of these were created the same way from 20 different samples, okay? And so what you see here is that with the 95, when we do a 95% confidence interval, what happens is if we do this, if we create a confidence interval this way 100 times, 95 of them will actually cover or include the true proportion. So that's what the 95% confidence level interval means. All right, so if we continue this, let's talk about some other notation there. We know what a confidence interval is. We mean if we follow this method that we've talked about, we will be right 95% of the time. We'll contain the proportion. We will do our job 95% of the time. So let's talk about some notation, right? We talk about critical values, and so critical values. If you look at this, this bell curve, critical values are these boundaries right here. They're going to be symmetrically placed, and we place them in such a way that there's alpha divided by 2 area here and alpha divided by 2 area there. So the total of those 2 alpha areas, if I add those 2 alpha divided by 2's, I get alpha. All right? So they're critical values so that alpha is the total of area, their boundaries, so that the total area in the 2 tails is alpha. All right? So that's what we mean when we talk about critical values. So let me just draw you a real picture here. Suppose I want to just draw a picture of critical values, which we'll label this z of 0.05. Okay, what are those critical values? Well, I know that 0.05. I know there's a boundary here, and I know that this area here is 0.05. Oops, not that one. Let's try that one. This area here is 0.05. Likewise, there's another symmetric boundary, which means they're going to be the same z-score, okay, just opposites, so that area is also 0.05, right? So those two will be the same z-scores. And if I look those up in my table, okay, if I look those up in my table, so that the area, so that I get those corresponding areas, I'm going to get this z-score is negative 1.645, and this z-score is positive 1.645. See how they're the same number, just opposite? And what's significant is that this middle area is 90%, is 0.9, right? If the two tails are 0.05 and 0.05, then that means the middle must be 0.90. So those are our critical values, right? They're the z-scores that divide our areas up like that, with 0.05 in each tail and 0.9 in the middle. These would be the z-scores that fit into your error formula. If you were making a 90% confidence interval, you will use these two z-scores, okay? So find the critical values, z sub alpha corresponding to 0.095 confidence level. So we're going to do this. I'm going to write it out, and then the subsequent slides will show you their work, but I just want to talk through it. So this is what I'm doing. 95% confidence interval, that means I've got a boundary here and a symmetric boundary here, so that this area in between is 0.95. Check again, grab the right marker, 0.95. Okay, so that's what it means. I need to find those two boundaries. These are the z sub 0.0. Well, I guess it's 0.025, right? Because 95% confident means that these two areas have to total to be 0.05, or divide in, or half to be 0.025. Okay? So what are they? I would look in my table. I would say, oh, look, there's an area of 0.025 right here to the left of that boundary. So I would look in my table and look up 0.025. Okay, 0.025, and I will see it to be right it's taking me just a moment. 0.025, the boundary is going to be negative 1.96, so this will be negative negative 1.96, and this one will be positive 1.96. Those would be my z's. Okay, actually z of 0.025. Okay, we use the positive version. Okay, so anyway, let's see them do this. Oh, don't do that. Why is that the case? All right, I don't like that. I'm going to copy it. I'm also going to lock it. Let's try that. See if that works. No, I don't need it to follow me down there. Let me pause this for a second.